So objective of this fragment is basically to understand the continuous random variable. Now we have in IB Math HL syllabus, we have the normal distribution, which is the core common component of both SL and HL. And we have a AHL component, that is your probability density function. So when you talk about, let's say, normal distribution or continuous random variable, now there are certain essential things that you got to understand before you do this part. So when you talk about the normal distribution, now normal distribution is you got to have the idea of firstly one quantity, which is the standard deviation. So when you distribute, or when you understand the distribution of normal on a variable, so it is x is distributed normally with mean mu and a variance of sigma squared. So this is the mean of the distribution, and this is the standard deviation. So when you have standard deviation, when you have larger samples outcome, like for example, if you're recording population of entire country and measuring their heights, you might not be able to express the individual probabilities using binomial and all for each data. So you have a bell curve. When you take a distribution, you get a bell curve, something like here. So the center of this is the average, which is mean of the data, and your standard deviation decides how much is the spread. So if your spread is higher, then your peak is going to be lower, and if your deviation is smaller, so it's going to be more focused around mean, and your probability will be all one, and will be calculated using the area under the bell curve. There is a specific function to represent this, so but we don't need to actually do that part for here. As far as the proofs and all are concerned, they can be assessed in paper 3, but now here in paper 2 and paper 1, you just got to understand the basics. So a normal distribution has like is always does depend on the mean of the data and the standard deviation. Now, before I go ahead, I would just want to clarify the standardized normal variable as well. Now, when you talk about what is standardized normal variable, so assume that there is a bell curve here for x distribution. Now this can be like any value, which is like 100, or like maybe it can be 100 to the power 10 to the power 8 as well. So this is like it depends on quantity to quantity. But there is a standard normal curve, which is the similar bell curve. But this curve always has the mean as 0 and standard deviation 1. So when you write down z is distributed normally with mean of mu and sigma square, and here mean is 1, mean is 0, and sigma is 1. So z is always distributed with mean as 0 and sigma 1. Now, what's correlation between z and x? So what we can actually do is we can use a formula that can convert x values to z values. So basically, it's like creating a clone for x values and use it in terms of z. So the formula that links both x and z is basically uh, x minus mean over standard deviation. So every x value you can see here, because mean and sigma is going to be same for a particular data set, we have one x value, one mean, and one sigma. So every x value has one z value. So basically, you're creating a clone for x value. I'm going to talk more in detail in later on. Now, let's just take an example. How do we use normal distribution to estimate the probability, and what are the other skills required? Now, I'm just taking one of the example, real life example. Now, let's say x is normally distributed with mean of 100, comma, variance of, let's say, 50. Now, always remember, this is, if I haven't specified a square term, this is variance. Variance is basically ST squared. So whenever you're finding out the probability for, let's say now, I wanted to find out the probability for x being higher than, probability for X being higher than, let's say 120. Or so in this case, my X value is going to be somewhere here. So this is 120. I'm just going to take this area. So this is the area that I have to calculate using my GDC. So now when you talk about the GDC, let's say before I calculate this probability, I want to also create a clone for this so we can do the calculations. So let's say if I have probability for X more than 120, can we convert to Z? Like how can this be converted to Z distribution? Now, what I can say is that let's say calculate Z value for X as 120. So Z is X minus mean over sigma. So X is 120 minus 100 over sigma, which is square root of 50. So that's your 20 over root 50. So this is your Z value for 120. So instead of using X now, I can use probability for Z more than 20 by root 50. So let's see how it comes. I'm just going to remember these values. So mean is 100. So mean is 100. The standard deviation is root 50. And my Z value is 20 by root 50. So let's just now do the calculations on the GDC and see what's the answer that I'm getting. So when we do the calculations on, let's say GDC, let's first see where is this feature. So you have to go under statistics. So under statistics, you go under distribution and go to normal distribution and pick up NCD. This is normal cumulative. So just rewriting the question what we had earlier, X is distributed normally with mean of 100 comma 50 here. And I had calculated probability. I had to calculate probability for X more than 120. And my probability for Z using Z was 20 over root 50. Let's see what both the answers coming to. Now, as you go here, you go click on NCD. So when you click on NCD, we get this kind of uh, statistics. So because you're using a variable, click on variable. So you can see here. So click on this variable. Now go on feed the lower value. So my lower value is 120. Now, since it is continuous distribution, you don't need to exceed this number like how you do in binomial and all. So don't take lower as 121 and those stuff, that then you'll make mistake. So lower is 120. And now, so if I have to just present it here, this is 120. Here is your mean. And this is the area that you have to calculate. So what I'm simply doing is I'm calculating the value of upper bound will be basically, you can take a higher limit for here. So I can just write down 10 to the power 5. My mean value that has been given in the question is 100 that I'm going to feed later on. First, you put standard deviation. So standard deviation is square root of 50 and mean is 100. So you can clearly see that the probability is coming as 2.2389 times 10 to the power minus 3. Now, what I want to do is I just quickly want to calculate the same stuff. I just want to remember this value. So I'll just write this down. It is 2.3389 times 10 to the power minus 3. So now this is the probability using the straight away the mean and the statistic that was given in the question. Now what I'm going to do next is I'm going to just simply calculate the Z using Z value probability. So when you calculate using Z value, let's see what do we get. Now instead of X value as 120, I'm going to put lower as 20 over root 50 since that's my Z value. And upper value can keep as it is because that's not going to affect. Sigma is 1 and mean is 0. Now, the interesting part, if you see, is that here as well, I'm getting the same answer. So I'm getting, let's say, 2.3389 times 10 to the power minus 3. So this is how you calculate the probability using the Z distribution and the X and normal distribution. So in the next fragment, what we're going to cover is how do we use the standard normal distribution to find out some of the critical quantities for a given data set. So this is it in this one, and next fragment will be on application of normal distribution.